Hello, everybody. Welcome back to Markov processes. I suspect there are a lot of questions on the homework, given how busy my office hour was. And there's certainly things that I wanted to tell you about the homework. Um, so one thing that we haven't talked about at all in this class, because it really doesn't come up very much for a statsy kind of class, is variance, the variance of a random variable. Hopefully you have seen variance before in whatever your prerequisite was, but I will just remind you that the variance of a random variable x, you find the mean for x. So a little locked up here. If you have a random variable x, discrete or continuous, with a mean or expected value mu, which is defined to be the expected value of x, then the variance of x, which is a measure of the spread of the distribution, is the expected squared deviation of the random variable from its mean. And if you square this out and run the expectation through and do those nice linear operator properties, you'll come to what is the much more commonly used in computation expression for variance, and that is the expected value of x squared minus the expected value of x all squared. So this is going to come up for us now, and actually in this homework, we need the variance for the Poisson distribution. And if you have x, Poisson, with parameter lambda, now this is not a process, there's no time here, this is just a Poisson random variable, then we saw last time that the expected value of x is lambda, and we could go through similar computations, they're a little hairier than last time, to find the expected value of x squared, but we'll ultimately be able to show that the variance for x is also lambda. And you can just use that as a given fact if you want. And this is one of the things that would be on the cheat sheet for the next exam, but we very rarely need variance. But you do in problem 5 on this homework, at least one way I can think of to do this. So if you wanted to find the expected value of x squared for a random variable, you could find it by integrating x squared in front of the PDF, or if it's discrete, putting x squared in front of the probability that x equals x and summing. But if you know the mean and variance for a distribution, you could always unravel the definition of variance and get this from the variance of x plus the expected value of x all squared. And so if x is Poisson with parameter lambda, the expected value of x squared is the variance for x plus the expected value for x all squared. And this is lambda plus lambda squared. So if you know the mean and variance for a distribution, this is the quick way to come up with the expected value of x squared without having to do a sum or integral. So check this out. If n of t is a Poisson process, so if is a Poisson process with some rate lambda, then we know that n of t itself as the number of arrivals or occurrences of whatever you're counting by time t, we know that this is a Poisson random variable with parameter lambda t. And that means we know that the expected value of n of t is just the lambda t. And doing what we did up here, we know that the expected value of n of t squared is lambda t plus lambda t squared. And how could this potentially help you in the homework? In problem 5 on the homework, you are given an s and a t greater than 0, and you want to look at the expected value of n of s plus t multiplied together. And these two random variables are really, really dependent. The number of arrivals at time s plus t includes the number of arrivals by time s and then whatever else came in. So very, very dependent. But if you want to take advantage of independent increments, you could write this as the expected value of n of s plus t minus n of s. And you can multiply that by n of s, and you'll see that the first term is what you want. And the second term, this minus n of s squared, is now in there, and you don't want that. So you can say plus n of s squared to get rid of it. This is the expected value of the, I can break it up at the sum. So n of s plus t minus n of s times n of s plus the expected value of n of s squared. And this n of s being n of s minus n of 0, you are talking about two increments of the process that are independent and can be pulled apart. And so you should be able to write down those expectations. And we just talked about how to get this expectation up here, although we used a t instead of an s. But yeah, this is hard if you don't know about variances, and we haven't talked about them at all, and we barely will. I was trying to avoid talking about them because we need them so little, but you do need them to solve this problem, I think is the best way to do it. Okay, so another problem left over from the office hour was the accept reject algorithm, which is problem 4 on the homework. Let's look at problem 4 on homework 5. Here you're trying to simulate from this distribution. It has a name. I wasn't telling you what that name is because I didn't want you to look up other ways to simulate from it. We'll talk about that later. I'm sure some of you know what it's called. But it is a distribution on the interval from 0 to 1, and you could have equality there or not. It doesn't matter. So I wasn't asking you to do anything optimal. If you look at this distribution, I don't know exactly what the shape is, but I do know that when x is 0, it's 0, and when x is 1, it's 0. So I do know it's tied down at these endpoints, and it does have one kind of like peak. Graph it and see exactly what it looks like. So when doing accept reject, you want to find an upper bound on this, and we call that g. And then you want to integrate that and get a constant and divide by the constant to normalize g into a PDF h that you can draw from. And anytime you're on a finite interval, a uniform distribution would work. I'm not saying it's anywhere near optimal, but the first thing I think of for a finite interval is to draw from h of x being the uniform 0, 1 PDF. So h of x is gotten by taking 1 over c times g of x, where c was defined to be the integral of g of x dx. And basically, let's look at this the other way. G of x is c h of x, and this has to be an upper bound on this function f. So maybe 1 is here, and this flat line is my h. And then g would be something that is the flat line multiplied by a constant. So you can find, if you want to optimize at least for this choice of a candidate PDF, you can get that g as low as possible by finding the maximum of this function. So this is some c. Yeah, you can. Like, do you mean bound it by something up here? Yeah, absolutely. We're going to see today that the expected number of steps to accept is, or sorry, the probability of acceptance is 1 over c. So if you go too high, you may have a hard time accepting, but yeah, you can eyeball it. What might be more optimal is kind of mimicking the shape, but we're not trying to be optimal. We're just trying to get some draws. And my advice on a finite support like this is to just use a nice flat line candidate. But then your algorithm consists of 3 steps. So step 1 is you simulate a y from the H distribution, which is just, in this case, uniform 0, 1. Number 2, you simulate a u independently from the uniform 0, 1. And number 3, if u is less than or equal to f of y over g of y, but g is this c, so f of y over c, then you output or accept the value y. And so the f function you are given, and the c you could find this c, or you can go a little bit above it by eyeballing it. So there's 3 steps to get one. Well, there's an accept reject move, but there's 3 steps with the goal of getting one draw. Draw a uniform, compare that uniform to this ratio. And if it's smaller than the ratio, you can output this draw. If not, start all over. And you want to get one output and then do that 100,000 times. I do want to ask you if you have questions about the homework, but I do want to say like a hint about really 2, especially like 2b. You really want to work not only the lack of memory property of the exponential, but also the fact that the minimum of exponentials is another exponential. So it does say, hint, take advantage of lack of memory, but recall that if x1 through xn are IID exponential with rate lambda, then the minimum of x1 through xn is exponential with rate n lambda. And so if you want to find, for example, the expected value of the minimum of these exponentials, it's just the mean for this exponential distribution. And in our notation, if the rate is n lambda, then the mean is 1 over n lambda. So how does this help you with a problem like 2b? For 2b, I would let C sub I be the time, not the total time, but the time at the pump for car I. So we have these random variables for I equals 1, 2, 3, 4. And the expected total time until the last car leaves, time until the last, departure here, it consists of several things happening. So first, you need one departure, and that's going to be the minimum of the times for car 1 and car 2. When one of them leaves, car 3 pulls in. So car 3 is now going to be racing against whoever was left and their remaining time. So when car 3 pulls in, what you have is a pump, and you have, I was saying in office hours, I can't draw cars, especially from the top. So this is like car 1 or 2, whoever was left after the first departure, and then car 3 pulls in. And so the first one to leave now is the minimum of the car 3 time and whatever is left over from the car that was left behind after the first departure. By lack of memory, that's just another exponential with rate lambda. So I would say this is the minimum of C3 and what I would call C. So C is the remainder of C1 or C2, depending on who left first. And that, by lack of memory, is this is still exponential with rate lambda, because we have interrupted an exponential amount of time. Like this car that was left over started with an exponential amount of time, and so did a car at the other pump. And then that one left first. And so the time left for this car is still exponential with rate lambda. So I don't know if it's C1 or C2 left over. I'm just going to let C be the remainder, or maybe C sub R or something like that, remainder time. So this first minimum is the first two cars racing. The second minimum is car 3 racing with the leftover time. And then one of those is going to leave, and we're going to have car 4 come in and race with another remainder. So I'm not saying these C's are the same. They're just the same type of random variable with the same distribution. And then when one of those leaves, we're going to have one more remainder time. Okay, so one of the cars leaves, and that's the time for the first car to leave. The new car comes in. This is the remainder time. The minimum of those is the minimum of 2 exponentials. So for example, for this first minimum is an exponential distribution with rate exponential with rate 2 times lambda. So I'm using the fact that the minimum of n exponentials is exponential with rate n lambda. So this thing in the circle here is 1 over 2 lambda. And so you just have to put all the pieces together. Yeah, you can do that. The max is harder, but you can absolutely do that. Rather than looking at the minimum plus the remainder, you could take the max of C4 and the remainder. That's absolutely valid. But the maximum of exponentials is not so nice. Okay, so I really want to launch into the Poisson process since we already started that, but I had to skip over the proof of accept reject. And so I don't want to forget to go back to that. So I know we're in the middle of showing a Poisson process is a Markov process, but let's just get the accept reject proof out of the way, and then we can do all the Poisson stuff we need to do. So this is the skipped proof that the accept reject works. And also we're going to figure out the expected number of steps for first acceptance and things like that. So I guess before proving this, I should remind you that we have some target that we want to simulate from, some target PDF f of x, or just f. This is what we want to simulate from. This can be discrete or continuous, and the accept reject algorithm will work. In my proof today, I'm going to use continuous notation, which is maybe the slightly harder proof. I don't know. Depends on your point of view. So you get a g of x that is above f of x for all x in the support of f, and I was calling this support S. And you compute c, which is the integral over the support of g of x dx, and you define, so this is not the proof, this is me reminding you of the algorithm, you define h of x to be 1 over c g of x for x in this support set, and this one is a valid PDF that integrates to 1. And then you do these steps. So you simulate or draw a y from the distribution with PDF h. You simulate or draw a u uniform 0, 1, and if u is less than or equal to f of y over g of y, it's a couple of ways to write that. G is c times h, so this is also f of y over c times h of y. Either way, you accept y as a draw from F, which means you output it, and that is your realization. And if the uniform does not fall below this thing, you have to throw out your Y and throw out your U and start over. So we have a target PDF that we want to simulate from. I'm going to assume, again, continuous distributions here. I'm going to let X be the output from the accept reject algorithm. So I'm not saying that X has PDF F, but that's what we want to show because that's our goal. So we want to show X has PDF F because that's what we're trying to simulate from. If X were discrete, I would start out by writing the probability that X equals X, and then I would write out what that means in terms of the accept reject moves, and I would try to get down to F of X. But because it's not discrete, the probability that X equals X for a continuous random variable is always 0, and the PDF does not represent that probability. So I'm going to start with the probability that X is less than or equal to X, because this makes sense for continuous random variables. And what I would like to get is the integral. Rather than writing this S, I think I'm just going to do everything on minus infinity to infinity. So I'd like to get the integral minus infinity up to X of the PDF. So if I start with this and I go through the accept reject rules and I see this is telling me that X had or has PDF F. This is what we want to show. Who's with me? All right, let's do it. This is going to be fun. I kind of want to condition on when the first acceptance is, because you have to go through potentially several trials. But rather than conditioning, I am going to just like put that in and marginalize out over it. So I'm going to write this as the sum as n goes from 1 to infinity of the probability that X is less than or equal to X, and the first acceptance is on the nth trial. So a marginal note, I didn't leave myself any marginal room, but to get that first acceptance, we're going to draw a Y, draw a U, draw a Y, draw a U, draw a Y. So I'm going to call those like Y1, Y2, Y3, U1, U2, U3, etc. And so the statement I wrote up here at the upper right, this is the sum as n goes from 1 to infinity of, so I have a bunch of failures and then the right thing happened. So I'm just going to write it like that. N minus 1 failures, comma, and intersection. The nth Y that I draw has to be less than or equal to X. That's the only way for the output to be less than or equal to X, comma, and the nth uniform I draw has to be less than or equal to F of Yn over G of Yn. And I could write out n minus 1 failures in terms of Y's and U's, but it's complicated looking and unnecessary. We will see. Also, in case I just switched there out of the blue, this is C H of Yn. Now, because the Y's and the U's are independent of each other and independent from trial to trial, we get that those n minus 1 failures are independent of what's happening in that nth time step. So by independence, this is the sum as n goes from 1 to infinity of the probability of n minus 1 failures times the probability that Yn is less than or equal to X and Un is less than or equal to that F over G, each evaluated at Yn. So I'm using the fact that what's happening in the first n minus 1 trials is independent of what happens in that nth trial. So let's zoom in on this probability. the probability that yn is less than or equal to x and un is less than or equal to f of yn. I think I'm going to switch over to the h notation. So ch of yn. To figure what this is, I have a couple of random things here. So I'm going to condition on one of them. I am going to condition on the value of y. I did, just to make this proof a little easier to write down, just assume that the support is minus infinity to infinity. So I'm going to go minus infinity to infinity. The probability yn is less than or equal to x. un is less than or equal to f of yn over ch of yn. Given that yn is y. Oh, I haven't reviewed this, or did we do it last time? Conditioning, I don't think I reviewed this. This stinks. I can't do this in the middle of the proof. Okay, aside, if you want to compute the probability that x equals x and things are discrete, you could bring in a y and you could sum out all those values. You could say the probability that x equals x given y equals y times the probability that y equals y. In the continuous case, you are not looking at the probability that x equals x, but maybe the probability that x is less than or equal to x or some other event involving x. And you could bring in the y PDF instead of the probability. So this integral is the sum, is going to become an integral. The probability will get conditioned on y equaling y. And the probability that y equals y is 0. It's going to get replaced by the PDF for y. I wanted to prove that before I started this proof. This is the analog of the equation above. And if anyone is wondering how y can equal y, I'm glad, because y is a continuous random variable. So the probability that y equals y in the continuous case is always 0. But you are allowed to have y equal, you are allowed to have an equal sign for a continuous random variable if it's to the right of a conditional line. We assume that we can measure our variables with infinite accuracy, otherwise they wouldn't be continuous. So in the example of measuring the height of the next person to walk into the room, the probability that they're exactly 68.29133510237 inches is 0. But once you've measured them, you have observed that actual value. And so you can talk about observing someone at an exact height. And that's why, so continuous random variables after a conditional line can have an equal sign. So I should really prove this, but I'm just going to go back to our proof and use this fact right now. And so that's what I did right here. From here to here, I conditioned on the value of y. So I let y equals y, and I kind of multiplied by the quote unquote probability that yn equals y, but that's 0. So really I had to use the PDF for y, and that was the h. So this is the PDF for any of the y's, in particular yn. Now on the probability part, I'm going to plug this little y in. This is the integral minus infinity to infinity. The probability little y is less than or equal to little x. Un is less than or equal to f of little y over ch of little y, given yn equals y times h of little y dy. The only random variable on this side is the uniform, and the only random variable on this side of the given line, that isn't equals, is the y, and the un is independent of the yn. So we do get to drop this conditional stuff now, since un is independent of yn. As far as the rest of it goes, this is weird. There's nothing random there. So that's like saying, what is the probability that 1 is less than or equal to 3 and something else happened? Or what is the probability that 3 is less than or equal to 1 and something else happened? if this is like 1 is less than or equal to 3, then the probability that this whole thing happens is just the probability that this happens, because 1 is less than or equal to 3, and you don't have to write that. But if the y is like 3 and the x is like 1, then the entire probability is 0. What I'm trying to say is this probability is 0 if y is greater than x. But if y is less than x, so we are integrating over y, so we'll go from minus infinity up to x. Then in that region, this is always true. And we're just talking about the probability that un is less than or equal to f of y over c h of y times h of y dy. This number is the same thing as f of y over g of y. And by design, because g was an upper bound on f, this is less than or equal to 1. And this is a uniform 0, 1. And you may recall that the probability that a uniform 0, 1 is less than or equal to u, this is going to be 0 or u or 1. It's going to be u if you are between 0 and 1. And it's going to be 0 if u is less than or equal to 0, and 1 if u is greater than or equal to 1. And so because our thing is less than or equal to 1, we're falling in here. And this is the integral minus infinity to x of just the argument, the f of y over c h of y, and then times h of y dy. And we get cancellation. And we get 1 over c, the integral minus infinity to x of f of y dy. This isn't what we started with. I took out a little piece and went all out on this side calculation. So we started with the probability that x is less than or equal to x, and we wrote it as the sum as n goes from 1 to infinity of the probability of n minus 1 failures times this other term that we just figured out. I want this to equal this. I don't want any of this other stuff here. And this looks like really bad to compute, but check this out. I'm going to take the limit on both sides as x goes to infinity. So the limit as x goes to infinity of the probability that x is less than or equal to x, this is going to be the limit as x goes to infinity of, this is, you could pull this all out because there's no n in that, of the, I'm just going to say right-hand side. On the left, the random variable x is always less than or equal to infinity. So this is a 1. On the right, I've got this failure thing. I've got a 1 over c, and I have an integral minus infinity to infinity of f of y dy, but that's a PDF, and this integrates to 1. So the stuff that's left tells me that c is actually equal to the stuff in those brackets, that ugly, ugly stuff in the bracket. How cool was that? We didn't have to figure out what this is, but we do know that this is equal to this. And so they're going to cancel. And what we're left with is this is equal to this, and that's what we wanted. So a probability that x is less than or equal to x is the integral from minus infinity to little x of f of y or whatever. This is the CDF of the target distribution. And this is the CDF of the output of the algorithm. That's how we define x. So we're outputting from the target distribution. And if you prefer to think in terms of PDFs, you could take the derivative of both sides with respect to x, and you'll get the PDF for the output is equal to the original given target PDF, which is what we wanted to show. I get my 2 lines that I always put at the end of a proof. And yeah, we did it. Okay, so what I can say is the number of trials until and except is or has the distribution has the distribution geom1, the geometric, with some parameter p, and p is going to be the probability of accepting on any one trial. And this is going to be the probability that a uniform is less than or equal to f of y over c h of y. And we can compute this by conditioning on y, given y equals y, and y would have the PDF h. And then I can plug in that lowercase y for the uppercase y's, and what's left on the left side, the randomness on the left side of the conditional line is the uniform, and on the right side is the y, and those are independent. So once I plug in the little y, I can drop this by the independence of y and u, and I have the integral minus infinity to infinity. The probability u is less than or equal to f of y over c h of y dy. This, by construction, is less than or equal to 1, and a uniform is going to be less than or equal to a number less than or equal to 1 with probability equal to that number. So I get some cancellation. I get 1 over c minus infinity to infinity f of y dy, but that's the integral of the PDF over the whole space, and that's 1. So 1 over c is the probability of accepting on any one trial. And so the expected number of trials until the first acceptance is 1 over p for that geometric, which is c. And so you can see this is why you don't want to take c to be too large when you're just trying to eyeball an upper bound. Okay. So we proved it. We got a sense of the acceptance probability and how it relates to how badly you've bounded the function. Along the way, I had to stop with a little aside about conditioning on a continuous random variable. And I should say more about that because we're going to seriously need that now, because we're going to take the Poisson process and try to figure out by the definition, the distribution of interarrival times. So let's talk about conditioning. This is another aside, conditioning on a continuous random variable. We talked about the bare minimum of how to get through the proof, but if we have a continuous random variable, so continuous x and y with a joint PDF, f sub x y of x and y, then we can talk about the marginal PDFs. So this is where you drop down to the PDF for x alone. And in the discrete case, we summed out the y's. In the continuous case, we have to integrate out the y's from the joint PDF. This is how you define the marginal PDF. And we can get the marginal for y by integrating out x. Okay, so from this, we can define conditional PDFs. But they no longer represent probabilities, so they're a little harder to interpret. Don't write this. This is not what I'm about to write. But we know that the probability that x equals x given y equals y is the probability that x equals x and y equals y over the probability that y equals y. And in terms of PDF notation for discrete random variables, we could call the thing on top the joint PDF or PMF over the marginal. And in PDF or PMF notation, the thing on the left, we can call the conditional PDF for x given y. And so these things are notation for these things. And this equality here is just the definition of conditional probability. But my point is that the thing down here is still how you define a conditional PDF in the continuous case. So the conditional PDF for x given y is defined as the joint PDF. I just can't call these probabilities, but it like mimics what you see in the discrete situation. So they're no longer probabilities, but that's still how you define the conditional PDF. And so if you want to find any probabilities for X in the universe where Y equals Y, so this bullet is just, I don't know, these are kind of random bullets. Random being street random and not Markov random or probability random. By random, I mean, I have no idea why I'm writing these things in this order, but probabilities for X in the Y equals Y universe can be computed by integrating this conditional PDF over whatever. So for example, if you want the probability that X is less than or equal to X given Y equals Y, and we already talked about why this is okay, even though Y is continuous, the probability you're going to observe that exact value is 0, but once you've observed it, you have in fact observed it. This would be the integral minus infinity to X of the PDF for X given Y. So you're still just going to integrate the X, and I don't know if you want to use a different letter. I mean, you can go ahead and use an X in here and plug in X. But computing probabilities for X in the Y universe involves integrating the PDF for X with that conditional Y equals Y coming along for the ride. And so I did claim earlier in my aside within the proof that the probability that X is less than or equal to X, we can get it by conditioning on Y. I claimed this was the integral minus infinity to infinity of the probability that, sorry about that, that X is less than or equal to X, given Y equals Y times the PDF for Y. But let's prove it. So a little proof here. I'm going to start with the right-hand side. The integral minus infinity to infinity of the probability that X is less than or equal to X, given Y equals Y, times the marginal for Y. This is a CDF in here for X in the universe where Y equals Y. So that is going to equal the integral from minus infinity up to X of the conditional PDF for X given Y. I guess I'll just use X given Y. dx Fy of Y dy. And if you pull this inside and interchange the order of things here, so minus infinity to X, minus infinity to infinity, I've got F of X given Y, X given Y, F Y, Y. I've interchanged the order, so dy dx. This thing, if you look at our definition now of the conditional PDF, is just the joint PDF. So minus infinity to X, minus infinity to infinity, the joint PDF for X and Y, integrated with respect to Y and then with respect to X. But this inner integral is integrating the Y out of the joint PDF. So this is minus infinity to X of the marginal for X, and then the dx is still sitting out there. And so we started with this funky thing up here, which I'm trying to draw an arrow to. It's not working. Okay, so we started with this thing up here, and what we ended up with is how we write the probability for X less than or equal to X. So we have just proven that this gives you this. But we are just kind of mimicking our conditional formula in the discrete case. So let's get back to the Poisson process. We had one definition, I'll call it definition 1 out of 3 of a Poisson process with a rate parameter lambda greater than 0. So it is a counting process, which means something that's just counting events as you're going through time. So it's a step function that is non-decreasing. The counting process, n of t, this is our continuous time notation as opposed to writing something like n sub t. And this is counting the number of events up to and including time t. And we have three properties to make it a Poisson process. One is that at time 0, we've counted 0 events. And I was saying last time that that's really a matter of convention and could be changed. The second thing is that we have these independent increments of the process. Increments. So I defined this with a whole list of t's last time, but let's say you have a t1 less than t2, so i.e. a t1 less than t2 less than t3. So you're looking at some time, t1, t2, t3. This independent increments property is saying the number of arrivals in here is independent of the number of arrivals in here. And those are corresponding to places where we step up. And so the number of arrivals in here is given by n of t2 minus n of t1. That's a random variable, and it is independent of the number of arrivals in here, which is n of the total by time t3 minus the total by time t2. So this is an assumption of the Poisson process. And finally, triple I is that the if we take it like an S and a T greater than, I'm going to say greater than 0 to be safe here. I really want to say like S greater than or equal to 0 and T greater than 0. Then N of S plus T minus N of S. This is looking at an increment of the process from some starting time S up to time S plus T. And this N of S plus T counts all the events up to and including S plus T. And this counts all the events up to and including S. So if you're being literal and, not worrying about things happening at perfect time points, this is the number of arrivals in the interval open S to closed S plus T. And triple I for this definition is that this has a Poisson distribution with parameter lambda times the length of the time interval, which is t. We were showing last time that this is in fact a Poisson process. And to do that, we have an ugly definition for a Poisson process in continuous time. So let's show this. Did I just say Poisson process? We were showing that it's a Markov process, and we have an ugly definition. So show that this is a Markov process. And we had a definition with like an S0 and S1 up through Sn, and then an S and a T, and an I0, I1 up through IN, and an I and a J. And the proof would be the same if I had all of those, but it was kind of too much to write. So I was just taking N to be 3, which still seemed like it was too much to write. I want to look at the probability that N at some time T is equal to J, given N at some earlier time S is equal to I, and N at some S3 is equal to I3, and N at some time S2 is equal to I2. And this would be a ... argument if we had N of these, but N at some time S1 is equal to I1. I want to show that that's equal to the probability of just this stuff. And so we wrote a big intersection over a slightly less big intersection. So this is just the definition of conditional probability. These time steps are assumed, they do need to be in order. So S1 is less than S2 is less than S3 is less than S is less than T. And I'm going to put this over the stuff after the conditional line. N of S is I, N of S3 is I3, down to N of S1 is I1. And then I want to take advantage of independent increments. So this is where we were last time. I am going to write the top probability. I'm going to start from the right-hand side and put N of S1 equals I1. But then the N of S2 equals I2, I'm going to replace with N of S2 minus N of S1 equals I2 minus I1. And I'll get n of S3 minus n of S2. I don't get any better at managing space. I'm going to start at the beginning here. N of t minus n of s equals j minus I. And then the one in between, n of S3 minus n of S equals the other way around, sorry. I minus I3. I didn't make this any better. I'm going to do the same thing on the bottom. This n of S1 is actually n of S1 minus n of 0. And so the random variables here, 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 and here, these are increments of the process. It's the number of arrivals between the various points in time. And all of those things I circled in yellow are independent. And therefore, I'm not even going to write out this denominator. You can break up the numerator into a bunch of probabilities. And you'll be able to do the same thing in the denominator. And the denominator will not have this last term because there's no n of t equals j here. So the denominator will have all of the yellow circles there except for the one on the left. And so we'll get a whole bunch of cancellation. This is going to cancel with this, and this with this, and this with this. And you're going to be left with just this one. See, I couldn't even bring myself to write it when n was 3, much less a generic n. But you're going to be left with this. And we started with kind of a big conditional probability. And so to show that you have a Markov property, you would say like, on the other hand, that's what I mean by OTOH. I would look at the probability that n of t equals j given n of s equals I. And I would write that out as the intersection that it is over the probability of the one after the conditional line. I did not mean a negative up there. That should be the intersection. This minus sign should be a comma. But we've seen to deal with Poisson, that should be equals j. To deal with Poisson joint probabilities, we rewrite them in a way to take advantage of independent increments. So we'll write this as n of t minus n of s equals j minus I, and n of s equals I, because that event in there is equivalent to this event up here. The probability that n of s equals I. And finally, we'll use independence to break this into two probabilities, after which we will cancel this one with this one, and we'll be getting exactly this back again. Did you sense my disdain for the process? I really didn't want to write this out. But that's how you would show that it satisfies the Markov process definition for continuous time in a discrete state space. Check it out in the typed up notes if you want to see more detail. Okay, let's do something a little more fun with our Poisson process. Here is some notation we're going to be using for quite a while, even after the Poisson process. And so this is, yeah, I don't know, notation for Poisson processes, let me say, because I'm going to be reusing letters that we've used before. So you do need to know the context when you see these letters. I'm going to let T1, T2, T3, etc. Now we've used this, right? Our TI used to be like first hitting times on a state I. We're in a completely different regime and context. And I guess I could use different letters, but there's just too many letters. We need to reuse some letters. And I also would like to stay closer to what you might find in books and on websites. I'm going to let these be the inter-arrival times for a Poisson process. If you draw the process, this is like counting a total number of arrivals by time t, and we're starting by convention with 0. And then at some random time, we're jumping up to 1. And at some random time, we're jumping up again. So we're getting like this step function thingy. And at some random time, we're jumping up again. And so this is T1, which turns out to be the time of the first arrival. But T2 is not the time of the second arrival. It's actually the inter-arrival time. And T3 is the inter-arrival time. And we could let, so I'm going to use this notation, Sn be the time of the nth arrival. And you can get that by summing the inter-arrival times up to, the first n of them. So I claim that these inter-arrival times have an exponential distribution with rate lambda. And if we can show that, we know that the sum of exponentials has a gamma distribution, and suddenly we're going to know a whole bunch of things. So I'm going to write that claim, and we'll prove it. Not only are they exponential with rate lambda, but they're independent. So I'm going to let this n of t be a Poisson process with rate lambda greater than 0. And the claim is that the inter-arrival times T1, T2, etc. These are IID, independent and identically distributed, exponential with rate lambda. So let's prove it. I'm not going to do a general inductive proof. All this stuff gets just kind of hairy. I'm going to look at T1 and T2, and we'll see it would just continue in the same way. So let's look at T1. And I want to know the distribution of T1, and I want to show it's this exponential. It's convenient for this, what we're about to do, to look at the tail probability. So let's consider the probability that T1 is greater than some t, where t is just, a real number greater than 0. I want to start with a Poisson process, and I want to show that this is like the tail probability for an exponential random variable with rate lambda. And so all I know is that I have a Poisson process. And the game to play is going to be to rewrite this in terms of the n of t. So if the first arrival happens at a time greater than t, that happens if and only if the number of arrivals by time t is 0. If the number of arrivals by time t is 0, then the time of the first arrival is greater than t. And vice versa, if the number of arrivals, if the time of the first arrival is greater than t, then the number of arrivals by time 0 is 0. So this is equivalent to saying the number of arrivals by time t is 0. And this has a Poisson distribution with parameter lambda t. It's an increment. It's n of t minus n of 0. So I can use that Poisson PMF or PDF, whatever you want to call it. This is e to the minus lambda t to the 0 over 0 factorial, which simplifies to e to the minus lambda t. And you might recognize that as the tail for the exponential distribution, but if not, turn it around. You'll get the CDF for T1 is 1 minus e to the minus lambda t, and you might recognize that as the exponential CDF. But if not, take the derivative on both sides with respect to t, and you'll get that the PDF is lambda e to the minus lambda t. And these random variables do live on t being greater than 0. So what we have just shown is, this is T1. We have just shown that T1 is in fact exponential with rate lambda. Okay, I'm going to go for T2, and then I'll just say ... because T2 is a little different. Let's do it. Let's go for T2. It worked out conveniently to look at this tail probability, and I'm going to do the same thing for T2. So T2. I want to look at the probability that T2 is greater than T, but this is not the time of the second arrival. This is an inter-arrival time. And it's going to be difficult for me to translate this to the N of T, the Poisson process, without knowing when the first arrival was. So I'm going to condition on the time of the first arrival. I am going to integrate from minus infinity to infinity. Our new conditioning trick, T2 is greater than T times the PDF for T1, which only goes from 0 to infinity. So I will write that. At some, I need another letter, so at some S. Oh, I totally forgot the conditional part. Given T1 is S times the PDF for T1 at S ds. And because T1 is exponential, this is going to be going from 0 to infinity because this PDF is going to be 0 for negative S's. So this is the probability that T2 is greater than T given T1 is equal to S times lambda e to the minus lambda S ds. Okay, so for this probability, let's draw a picture of the arrival process. I know that the first arrival happened at time S, and I want the probability that T2 is, so I want the probability that the inter-arrival time is greater than T, meaning the time of the next arrival is greater than, is somewhere up here. So if this is time S plus T, I want the next arrival to be greater than that time. And going back to the N of T process, this is the probability that the number of arrivals between time S and S plus T, which we can write as the number by time S plus T minus the number at time S, we want that to be 0. And the rest of this stuff, lambda e to the minus lambda S ds. So same kind of idea. We know things about the Poisson process. We're trying to show things about the inter-arrival time. So I am trying to interpret things like this in terms of the Poisson process. And this is a Poisson random variable with parameter lambda times the length of the interval, which is t. And so we get 0 to infinity, e to the minus lambda t to the 0 over 0 factorial, and then the lambda e to the minus lambda s ds. This goes away, this goes away. This doesn't even involve s. This is e to the minus lambda t, the integral from 0 to infinity, lambda e to the minus lambda s ds, and this is 1. We're integrating that exponential PDF. So I get e to the minus lambda t for the tail probability for T2. And so the probability that T2 is less than or equal to T is 1 minus e to the minus lambda t. And so we can see that T2 is exponential with rate lambda. And I need to convince you next time that they're independent. I think you can kind of maybe see like things are just pulling apart and separating, but I do need to convince you that they're independent. And then I'll just say ... for the remaining t's. So I am out of time, but you know what? The time of the nth arrival, like if it's customers coming into your store, the nth customer will come in after a gamma amount of time with parameters n and lambda because it's sum of n exponentials. It's going to be super cool. Please come back. I mean, I don't even have to ask. I know you're coming back for this stuff. So yeah, next time on Markov processes.